Hello everyone, welcome to the class of Artificial Intelligence and Machine Learning. I am Ram Nivas from Department of Electronics and Communication Engineering. In today's class, we'll discuss about advanced machine learning techniques. Starting with ensemble learning. Ensemble learning is a supervised learning technique which is used in machine learning to improve overall performance by combining the predictions from multiple models. Here we have averaging, bagging, boosting, blending, and random forest. So in boosting, we'll see about gradient boosting. This is a powerful machine learning technique which is used for both regression and classification tasks. It builds a strong predictive model by combining multiple weak models, usually decision trees, in a sequential way. Instead of building one core complex model, gradient boosting builds models step by step, where each new model tries to correct the errors made by the previous one. The name comes from gradient descent because it minimizes the loss function by moving in the direction of steepest decrease gradient. Let's see how it works. It will start with a simple model like predicting the mean. It will calculate the average, that is nothing but the residuals, and train the new model to predict these errors. Add this new model to the previous one and repeat the process to reduce error gradually. Now this is the mathematical expression for gradient boosting, which is like updated model is obtained from new weak learner and learning rate and the previous data fm minus 1 of x. The advantages are it is highly accurate, it works well with complex data, it handles different types of data, numerical and categorical. For example, uses used in fraud detection, image classification, medical diagnosis, and stock price predictions. And the disadvantages are it is prone to overfitting and computationally expensive and sensitive to noise. Let us consider an example data set of house pricing and sales decision. Our goal is to predict the house pricing, which is a continuous value, and the given features like area, bedroom, age, and distances are given, and we need to predict the price of a house. Right, with the for predicting the price of the house, we need to sum up all the values of the previous cases like 50 plus 80 plus 65 plus 90 divided by 4, which is giving you the predicted f naught value. So the actual value and predicted value is having a difference, so the residual is obtained from subtracting actual value and predicted value. We are getting this residual. This is your first iteration table. So in the first fit first weak learner H1 is to be computed. If the area is less than 1600, the prediction is minus 13.75, else the prediction is plus 13.75. So choose a split, like if your area is less than 1600 means you choose it as a left node. If it is greater than or equal to 1600, you can choose it as a right node. If the left node area is less than 1600 and right node area is greater than 1600, we are obtaining this followed residual, and the residual is obtained by adding them and dividing them by 2, that is midpoint value. We are getting it as residual values, and the final weak learner H1 is computed. Then mean is to be computed. This comes from minimizing mean square error. And updated model formula is written like f1 is equal to f naught plus 0.1 into h1, where gamma, which is equal to 0.1, is your learning rate. And computing new residuals, and the process continues in step 3 and step 4. And fit second week learner is identified with this by the new values of new residuals or new updated values, and the updated model is yielding you the new f2 values. So we can get the final insight of prices values, and f of x formula will be equivalent to cost plus tree 1 plus tree 2, and number of trees, the number of iteration, it goes on. So the gradient boosting, after performing 5 iteration, I am getting this value. By the convergence observation, we can find that 71.25, which is a constant, is a high error, and 69 to 72 is a reduced error. 67 to 75 is a better value for your apartment, and 65 to 76 is approaching the actual value. So from this, each iteration reduces residuals and it updates move prediction towards the actual value, and convergence is gradual due to learning rate, and the final model will be equal to the number of weak learners. Okay, so the gradient boosting works by minimizing loss using gradient descent, where each steps moves in the direction of reduced error. At each stages our error is getting reduced. Now we will see about the bagging and boosting techniques. So bagging and boosting techniques are the categories of ensemble learning. Bootstrap aggregation is known as bagging. It is a machine learning ensemble meta algorithm designed to improve the stability and accuracy of machine learning algorithms like classification and regression. It decreases the variance and helps to avoid overfitting. It is usually applied to decision tree methods, and bagging is a special case of model averaging approach. And random forest is also commonly used in machine learning. We'll see about it later. And bootstrap sampling, train multiple models, and aggregation are the steps in bagging. It improves model accuracy, reduces overfitting, simple and easy to implement, and works well with noisy data. And the disadvantages are increased computational cost, less interpretability, and not very effective for low variance models. And this is the mathematical representation of it, and this is a real-time example of it. Here the original data set is there, and the original data set is made into bootstrap samples of D1, D2 and D3, and the combined result of the bootstrap samples will give you the final prediction or approval. Here I am getting votes from D1 and D2, which is the majority vote. The multiple models are trained independently, and aggregation or voting or averaging is performed, and models H1, H2 and H3 are employed in the process. Depending on the highest vote, my final prediction is obtained. So this is for a loan approval application. Here is the loan approval original data set. Now we are categorizing them to bootstrap data 1, data 2 and data 3 and data 4. And the problem statement is loan approval prediction is in bank will predict the whether the customer will be repay the loan or not, and challenge is that data is noisy and highly variable, and small changes in data and different decision tree, it will lead to high variance, and the final decision should be stable and reliable. Now your bootstrapped samples are entering the decision tree 1, 2, 3 and 4, and the decision trees are giving you the final predictions. Out of this, 3 decision trees are giving you the prediction as approved, and 1 decision tree is giving the prediction as rejected, and from the aggregation and majority voting the final decision is approved because it is satisfying the 3 categories out of 4 in a better way. Only one is getting rejected. So one tree may wrongly classify a customer, another trees are correctly classifying the customer. So final decision is stable and reliable. So this is a problem statement where D1, D2, D3 and D4 are the data sets of customer record, 4 bootstrap samples which are created, and they are used to train a decision tree classifier H1, H2, H3, H4, and we are having the predictions like +1 approve, reject, approve and approve. Now for classification, I am summing up all them. So sign of +1, -1, +1, -1. So finally I am getting the +1. So the finally the answer is loan is approved. And interpretation, even though one model is mislead classified the customer, majority of the models are predicted correctly. So the bagging gives you a stable and reliable decision. Next is bagging. Now we'll see about bagging. The bagging, the same example like loan approval prediction in a bank. Will the customer repay the loan? You can accept or reject it, accept or reject it. And from the original samples, the same way I am performing the bootstrap data D1, D2, D3. Here my process is not parallel, it is serial. From D1 it is going to D2, from D2 it is going to D3, from D3 it is going to aggregation or majority voting. From there I am getting a model, my results will be passed to model H1, H2 and H3, and depending on this my final decision is made. So now we'll get to know about the boosting techniques. The boosting in ensemble learning method where multiple weak learners are trained sequentially and each new model focus on correcting the errors made by the previous ones. Combine several weak models to form strong learners by giving more importance to misclassified data points, training models after one another sequentially. So we'll see about the steps in boosting. First, weights will be initialized, train weak learners, evaluate the errors, update weights, repeat, and final predictions. And this is the mathematical model for boosting techniques, and this is the formula for it. And we have popular boosting which are used are ADA boosting, and gradient boosting, and XG boosting, and these are the key features, and they are dependent, hard to classify samples, and reduces both bias and variance. And advantages: it is highly accurate, works well with complex problem, it reduces underfitting. Disadvantages is it is sensitive to noises, outliers, and can lead to overfitting if not tuned. Computationally it is expensive. Model 1 classifies some points and it is giving to the model 2, and the model 2 focus more on these errors, and model 3 further improves, and final output is the combined strong prediction. So this is the same example of loan approval prediction. Now we can see that train a sequence of weak models and each model focus on correcting the mistakes of the previous model and combining weak models for the final predictions. Now the weak model 1 focuses on mistake and higher weight it is given to the model 2, and it is eliminating the mistake and it is fine tuning and aggregation is performed and final prediction is done. Now this is the real-time example of fraud detection in online transaction, and fraud cases are rare imbalanced data set, and subtle fraud patterns are hard to identify, and simple models miss difficult for fraud cases. So the process is: train the first model, detect easy fraud cases, identify misclassified transactions, increase their importance, train next model, focus on these hard cases, and repeat the combining models. Now the aggregation is performed plus weighted majority voting is done. If fraud is identified, then it is labeled as fraud, and if the final prediction is good, then it is legit. So final system will be highly accurate fraud detection system because it is passing through multiple models. As a result of this, fine tuning is done, and my final result will be a better result. So this is what a practical example of it. Your x1, y1 values are given. All sampled equal weights are calculated. 1 divided by 4 will yield you the 0.25. By following multiple iterations, we will be getting the final strong classifier, and final decision for a new customer is derived. So as a result of this, a loan can be approved or rejected. If majority of the classifiers are giving you the good result, then your loan will be approved, or else your loan will be rejected. And the boosting build model sequentially and combines them mathematically using weighted sum to reduce errors and improve the accuracy. So this is how the iterations are working, from iteration 1 to iteration 2, followed by final combined model and your prediction table. Now we'll see about the support vector machines. So the support vector classes are given. From the support vector classes, midpoints of the support vectors are calculated. Midpoints will be like 3 comma 3.5. Direction between the points are also computed, so which is 4 minus 2 and 5 minus 2, which is through 2 comma 3, and the equation of hyperplane is obtained from substituting the values of support vectors and direction vectors, and the final separating hyperplane is derived like this. Now we'll see about the next problem on choosing the best hyperplane. The given classifiers are given, classifier 1 and 2, and to find out the best hyperplane, the classifier 1 is related with general SVM hyperplane, and W values and B values are extracted from the equations. Now we are going to compute the margin, which is 2 divided by omega. So we compute the magnitude of weight vector. So W or omega is equal to square root of the two values, 2 square plus 5 square and 20 square plus 50 square. We are getting this margin 1 and margin 2 values. By computing the denominator of margin 1 and margin 2, we are getting the results like 0.372 and 0.0372. From this we can find that margin 1 is greater than margin 2. So the best hyperplane is the first equation. The given hyperplane is given. Find the perpendicular distance between the points 1, 1 from the hyperplane. Determine the margin of the hyperplane and write the general formula used for computing. So this is the expression. Now the values are from general hyperplane expression. I have derived the values of 2, 3 and b is equal to -6, and distance between the point is computed by w dot x plus b divided by double line pipeline symbol of w, which is by substituting the values and simplification I am getting the values of square root of 13, and my final answer is 1 divided by square root of 13. The margin of hyperplane is computed by 2 divided by omega, which is equal to square root of 2 square plus 3 square, which is equal to square root of 13. So the margin is 2 divided by square root of 13. Now the last topic of today's class is reinforcement learning. Reinforcement learning completely depend on agent and environment. So agents are nothing but the learners or decision makers, and they'll perform actions. Where agent operates, state provide rewards, and actions are nothing but the rewards or penalties. And the goal or objective is to maximize cumulative rewards over a time. So agent will perform an action on environment, and environment will react back to the agent. Now the types of RL are model free and model based. When it is a model free, it learns directly from experience, and model based builds a model of the environment and plans before execution. Few of the algorithms are SARSA, Q learning, and deep Q DQ network. And pros and challenges: learn from interaction and adapt to a dynamic environment. It's slow in convergence, exploration with exploitation, trade-off will be there, and complex environments are hard to model. And it is mainly applied in self-driving cars, robotics, and game playing. And it is also having applications in robotics and self-driving vehicles. So this is an example of it. Agent want to meet the reward, and the environment he need to perform the actions. If he is facing the obstacle, then it is a false case. If he is not facing the obstacle, then it is a true case. Agent has a policy, and he performs the action in the environment, and environment will give the agent back the observation. And again, from the environment, reinforcement learning algorithm will get the rewards and update the policy. If there is a penalty also, then it is updated in the policy, and the process is cyclic and it will continue. It is in a feedback loop format. So step-by-step interaction. For example, let us consider a real-world scenario of a self-driving car. The steps in self-driving cars are: agent observe the state, agent takes an action, agent response, or sorry, environment response, and agent receives reward, and agent updates the policy, just like what we have seen in the previous case. Here the agent is self-driving AI system, and environment is road traffic and pedestrians, and state is car position, speed, and nearby vehicles, and action is acceleration, braking, and turning, and rewards are +10 for safe driving and -100 for collision, because -100 is given maximum weightage because it is highly risky. The interaction cycle in this example is car detects the surrounding, decides to move forward, environment changes, and receives reward, safe positive reward, and improves the driving strategy over time. So this is how it is implemented. So driving situation or the environment is detected, and inputs are obtained from camera, lidar, radar, GPS, IMU, HD map, and vehicle state, and it is fed to the RL network. The model based RL, meta RL, inverse RL, and conventional RL all are there, and it is given to actuate the steering, acceleration, waypoint, cost map, and vehicle. Here our agent is car, and it is giving action to the environment, getting the rewards, and moving to the next state. This is the block diagram where sensing camera followed by autonomous perception, trajectory planning, vehicle kinematics, and dynamic model and control commands to the driver where the actuation is happening. So this is the real-time image of self-driving vehicles. So action, reward, observation, and then the actions like turn left, turn right, brake, and accelerate, and the surrounding people interferences all are obtained here. And that's the end of today's class. Thank you.